Hello, welcome to Streams and Flooding. Our main goals today are to understand the different features and characteristics that make up a stream, the processes that create and destroy them, and how we interpret the flooding of a stream. Scientists classify a stream as any amount of water flowing through a channel of any size. When the channel and water flow amount differ, we often assign the name river to a stream of larger size. Although rivers possess characteristics of streams, the main distinction is only the name and the size. Many famous topographic features were formed by streams, such as the Grand Canyon and the Mississippi River Delta. The features that make up a stream are controlled by processes called erosion and deposition. Erosion occurs when running water moves or strips away rock particles, sediments, and soils that line the stream. In order for erosion to take place, the velocity or speed of the stream must be high enough to move the sediments sitting along the stream. While the water possesses the power to move these sediments, it can also place them elsewhere if the stream conditions are suitable. Deposition occurs when the velocity is slow enough in the stream, the sediments being carried by the water are able to settle out and become placed along the stream bed and sides. Within a stream, there are usually multiple areas of both erosion and deposition. Now, to understand the flow of the stream, scientists use data such as discharge, or the volume of water that flows past a given point in time, often measured in cubic feet per second, or CFS. Scientists also use the gradient to gain a better grasp on how much water is moving and how fast. We can find gradient by taking the change in elevation and dividing by the change in distance, giving us the slope of the stream, feet per mile, rise over run, y over x. Different natural locations will have varying features, such as a mountain stream, which often possesses narrow V-shaped valleys and correspondingly shaped streams with higher gradients. Areas such as southern Louisiana with the Mississippi River flow along an even surface, will exhibit wider channels, low gradients, and a meandering stream that winds back and forth across the open plains. In our Stream 101 basics, we consider the base level of a stream the lowest level a stream can erode its channel. Base level is often connected to sea level, otherwise known as ultimate base level, or where a stream ends and flows into a lake or a larger stream, temporary base level. As we previously discussed, the passage of water through a stream has the ability to erode and deposit sediments. Different stream environments with different stream channel sizes, velocities, discharge, and gradients create streams with different features. Geologists back in the late 19th century proposed a stream erosion cycle to explain differences in streams and stream features. The cycle was defined to have 3 stages: a youthful, a mature, and an old age stage. The general premise of the stream erosion cycle is a good start to describing the changes stream erosion can cause over time. Today, scientists understand that parts of a stream can progress through different stages at different times, and the stream cycle erodes in different ways. For example, an individual stream that begins way up in the Rocky Mountains in Colorado would have features in the youthful stage at the stream's beginning, and by the time the stream has reached the Gulf of Mexico, it would resemble more of an old age stream. Factors such as precipitation, vegetation type, rock type, and resistance to erosion all play a factor in the erosional cycle of a stream. As processes alter a stream, there are a variety of stream features that may be created. The diagram here points out a few. We use the term head to describe the beginning of a stream, where it starts, and the term mouth to define the end of a stream, where it ends, either by merging into another larger stream or a body of water, such as a lake or an ocean. A meander is considered a bend or curve in the stream, and a meander has 2 parts, the cut bank and the point bar. The cut bank is considered the outside edge of a stream, where erosion occurs, and the point bar is the inside edge of the stream, where deposition occurs. Now this happens because the velocity of water around the outside of the stream is faster than the inside curve. So the faster water erodes while the slower water deposits. You can think of it as a race around a running track, with people running around the outside edge have to move much faster to keep up with the people running around the inside. We also have a feature called an oxbow lake, which is formed when a meander is cut off from the stream pathway after deposition around that inside edge has diverted the channel in another direction. It results in the small crescent-shaped lake you see down on the right on this diagram. Although not shown here, another feature important to stream processes is a delta. A delta is a landform created by the deposition of sediment carried by a river as the flow leaves the mouth and enters slow-moving or stagnant water. An easy example of this is the Mississippi River Delta, which is formed where the river ends and empties into the Gulf of Mexico. Finally, our last common term is a floodplain, which is the land surface around the stream that would be affected if the stream were to overflow and flood. This is largely dependent on the elevation outside of the stream and how the gradient is in the surrounding area outside of the water levels. Since we've covered stream terminology, we must also cover stream transport. When sediment particles or rock fragments are moved through a stream, there are three main ways the stream can transport the sediments. Suspended load are particles that are carried by the stream, held up in the water, but not dissolved within the water column. Bed load are particles that are too heavy to be held up by the water, and they move by sliding, rolling, or bouncing along the stream bed. Dissolved load are particles that are carried by the water in solution. Now you may ask, as you move downstream, how does this change the particles? Generally, we see a decrease in particle size, and if you remember way back to our sedimentary rocks, when we discussed the properties of rounding and sorting, sediments further downstream will be more rounded and often better sorted. Scientists can use these properties to help determine where the stream sediment originated and how far it has traveled. The last topic we will cover today is flooding. Flooding occurs when there is more water in the stream channel than the channel is able to hold, known as the flood stage. However, flood stage is only determined by its impacts on humans and infrastructure, not on surrounding topography where the general population does not reside. Flooding to a large enough extreme can be devastating to the local area. Floods can ruin houses, wash away roads, bridges, and affect the drinking water supply. In the US alone, floods cause on average 82 deaths each year and almost $4 billion in property damage, according to the NOAA flood loss data. To mitigate floods, engineers have developed structures such as flood walls, dams, dikes, and levees. By collecting all this data, such as stream discharge and velocity we discussed about earlier, scientists can create rating curves to predict how high the floodwaters will reach and predict how often floods of certain magnitudes will occur in areas to help us better be prepared in the future to avoid any damages caused by floods.